That was a kind of a good segue. There was lots of interesting data there about the transition to cloud. And I was at the Open Source Business Conference last week where James Staton gave a talk. And he said that 70% of cloud applications today are forklift. They're sort of standalone single systems. 20% are auto-scaled or elastic, so they're a bit more than forklift. And 10% are cloud native. So what I'm going to tell you today is what is cloud native and what is going on in that 10%, because that's kind of where we are, and we're sort of leading the field to some extent and sharing what we're learning to do cloud native. Most of the money right now is in that 70 to 90% of people trying to get forklifted code to work. But I think the future is going to be in cloud native, so take this as kind of a directional thing probably. So I'm go first of all explain what do we mean by cloud native, why do we do it, and then talk about a little bit about our open source software that we've done which helps people get onto cloud native. And a lot of you I know are sort of PaaS vendors and software companies on your own. I'd like to encourage you to look at this as components that you can adopt to help your applications sort of adopt some more of these cloud native natures. And then at the end, we've got a prize running right now, so just quickly explain what we're doing with that. So to start off with, most of us, anyway, I'm not sure how many people here are engineers, but we're engineers, solve hard problems, build amazing things, and fix things when they break. That's kind of the nature of engineering. And we're always looking for perfection. We want perfect code running on perfect hardware that's perfectly operated. That's the utopia, the nirvana of engineering. But it takes too long. You're always, there's a deadline, you've got to get the software out, so you compromise, and you're always doing time to market versus quality, and this utopia is out of reach. So in some areas, I mean, if we're delivering packaged software, that's shipped on CDs or DVDs, you're making millions of them, it's expensive to make a mistake. So you have to take time, and we're moving from a world where that's the default to a world where web services are the default. I think I heard a few days ago that Adobe is shutting down its packaged software and is delivering everything as a service. So this is the transition that's happening. We're also using agile infrastructure, which is really what cloud is, and we're moving to continuous deployment, so we're updating our systems all the time. So what do I mean by soon? Right? Instead of working on some code for 9 months to get it perfect, what we really want to do is think up a code feature and ship it in days. From the time you thought about it to the time customers are using it. We measure that in days. When we want some hardware provisioned, we do that in minutes. From thinking, yes, I need some hardware now, to the time when that hardware is up and running our code. And when something goes wrong, we want to detect that it went wrong in seconds and respond and fix it in seconds. So that's, days instead of months, minutes instead of weeks, seconds instead of hours. That's the new sort of agile cloud native nature of what I'm talking about. And what that means is that it tips this balance from the utopian world where we want everything to be cheaper and better and static and stay the same so we can manage it, to a world where we don't really mind if it's inefficient, we don't really mind if it's broken some of the time. Everything's dynamic, you don't really know the state of anything in the system, but you get it so much sooner that it tips the balance, and this is where you get your business value. So we're living in what I call, I did a talk a few weeks ago called Dystopia as a Service that I introduced these slides at. So this is the new engineering challenge. We're trying to construct this highly agile and highly available service out of ephemeral, meaning they come and go and leave no trace behind them, and often broken components because we're shipping broken code all the time. We just don't have time to fix everything. But what we want to do is build a highly reliable service out of these components. And I'm going to explain briefly how Netflix streaming works so we can explain how we do this. So it's a cloud-native application. Those of you who have Netflix accounts, this is kind of what the homepage looks like. There's a whole load of rows of movies. They're chosen for you when you log in. They're specific to you. And you can see here I have a Facebook row of my friends. So this is all very personalized. The way that works, there's a customer device shown in blue. That talks to, it's either a website if it's a browser, or it's talking to a Discovery API. All of the yellow boxes on here are running on AWS. They're all cloud-based services. So that figures out all the user data, does all the personalization, comes up with lists of movies for you. When you hit the play button, it clicks over to the streaming API, which does DRM, gets you all of the data you need to play that particular movie, and then does lots of quality of service logging so that we can figure out whether everything's going well. Did you rebuffer? Is this movie broken? Or is there something wrong with the encode? All those kinds of things. Then the bits themselves are delivered from Open Connect boxes. This is the Netflix CDN. We kind of outgrew Akamai, Limelight, and Level 3 as CDNs, and we wanted something that was a small proportion of their functionality at a much higher bandwidth, and it ended up that it was better to build our own for that. And then behind that, there's a bunch of AWS-based services that do management and steering of the CDN, and then we ingest all of the content from studios and encode it into all the different versions we need on AWS and put that into the CDN. So that's the whole environment. There's no box on here marked data center. So this entire flow, this is the regular flow of our users that happens every day. Billions of views a month are running through this. Now, none of what they do touches the data center. Now, the sign-up flow does touch the data center because we haven't quite finished moving all of our credit card processing into the cloud, but we're working on that, and that's probably going to happen in the next year or so. So this is the real version of that. We're talking a bit more about how can you measure this. This is using App Dynamics. This is actually the flow of requests for all the internal services that make up the Netflix homepage view. So this is a single view of the homepage, that screen I showed you. And this is how many services are involved in it. I haven't even counted these. There's probably 50 or 100 distinct services that are invoked. Every one of the little boxes here is typically hundreds of individual machines spread across 3 data centers. And some of them are Cassandra backend databases, some of them are memcaches, some of them are S3 buckets. So there's a bunch of things going on here. So just to give you some idea what it actually looks like. And if something fails, we just turn off that piece of functionality. So this is one of the ways in which we deal with broken code is if somebody updates a service and breaks it, the website just adjusts slightly and you get slightly worse recommendations, but most customers can continue to use the service. So when you look at that from a deployment point of view, we have all these things in the clients. Behind them are lots of auto-scale JVMs with Java Shop and caches and things like that. And everything's organized in 3 columns here because I have 3 zones. These are AWS Availability Zones, which think of them as data centers, separate buildings a few miles apart. And all our data is written across these 3 data centers. And this is the backend that Cassandra gives us as a data storage platform. It's basically replaced Oracle and things like that, and MySQL as our base store for all of our data about customers and all the things we need to know. When you write, you try and write to all 3. If 2 writes succeed, you're fine, you move on. When you read, you need a 2 out of 3 as well. So you can do a consistent read after write and get the consistency you sometimes need by doing quorums. There's no master and no slave here. So it's a very different architecture to the typical sort of MySQL master-slave or MongoDB master-slave kind of model. Now, if we lose an entire data center or entire zone, everything keeps working. This causes a few retries, our error rate spikes a little bit. We can lose 1/3 of our infrastructure without having any customers call CS. That's our measure of success for availability is, did customers notice enough to call CS? And we ran a test like this about 2 or 3 weeks ago where we actually deliberately turned off 1/3 of our infrastructure. We deliberately killed an entire zone and ran on 2 zones for a while just to prove that we could do it. And we found a few things. We had a few more errors than we expected, and we fix those and move on. But unless you test this kind of thing in production, you don't know that it works. This is a pretty radical kind of approach. We've talked previously about Chaos Monkey, which is a service that kills individual servers. This is the Chaos Gorilla, which in this particular instance killed almost 3,000 servers in one go. Because this is the total environment at that time was around 9,000 machines. Now, if you have a non-native cloud architecture, this is what I'd call the forklift or the probably this is more like the elastic architecture. You have some stuff in your data center, some legacy apps, some MySQL, I call them data center dinosaurs. Somebody says, hey, we have to deal with all of these tablets and phones and things, and we want to put up an application, and you build but you don't have enough agility to deploy that in your data center to keep up with the mobile apps. So what we typically see is that there's a bunch of app servers running in the cloud, back-ending into the data center, and supporting mobile type of applications. And that's a fairly common pattern now, and that's what I'd call, it's cloud architecture, but it's not what I'd call a native cloud architecture. And typically what happens is if anything goes wrong, you've lost the whole thing, and your apps are sitting there with some kind of failure, error message on them. Because it's hard to build enough replication into this to actually get it to survive outages. So what are these patterns? We've got microservices, like I showed you. There are lots and lots of single function services. We have chaos engines that are killing these services off to prove that they're resilient. When we're building highly available systems out of these ephemeral components. And then the other thing is that open source is the default here. Just about everything we do is based on open source. We're open sourcing what we produce, and there is very little enterprise or supplier software in there. There's a little bit around the edge. We have some vendors of things like security products that we use for certain point solutions in our cloud, but the big enterprise vendors of hardware and software are nowhere in this architecture. And that's one of the reasons why you see the big sort of implosion that's going on right now in the enterprise IT space as the big companies are trying to figure out where all their revenue is disappearing to. So cloud native. Master copies of my data are in the cloud. I don't have another copy of this in the data center. I have to do backups from the cloud. Everything's dynamically provisioned. I can make a new Cassandra cluster in about 10 minutes. I did that live on stage last summer at the Cassandra Summit. I ran a benchmark where I created a cluster, doubled its size, ran some more tests on it, and then shut it down again live during a 1-hour presentation. And I did 2 clusters side by side and ran a test there. And all services are ephemeral, including the data services. So it's a fairly radical difference from the typical data center model. So how do you get there? How many people here are running cloud native today? No one? Maybe 1 or 2? How many people want to get to cloud native? We get a few more hands, otherwise I should just go home. Okay. Everyone's still there and awake, have enough coffee. So the way you get there, and I'm going to talk a bit about the transitional phase we went through, is the first thing we did is we have a freedom and responsibility culture, but you have to apply that to your developers. You have to give them the freedom to deploy the hardware themselves and deploy their own software, but then they have the responsibility for keeping it running, meaning that they're on pager-duty and they'll get a call at 3 a.m. if their app broke. So they're not always comfortable with the responsibility, but they like the freedom. So if you give them both, that's one of the key ways you get there. We decentralized and automated all of our operations activities. Now, there have been some debate over what you could call this. It's really a version of DevOps, but some people call this no-ops because there's no ops organization, but there is ops going on. What we basically mean is the developers operate stuff themselves, and the operations organization is distributed amongst the development organizations. It's part of that responsibility. So you take this DevOps, developer and operations, which is now integrated, and we also integrated it into the business organization. So the line of business is driving all of the development and all the operations of all of its infrastructure. So I call that biz DevOps or something. We could pick a new name for it. So that basically means a reorg. And back in 2009, we effectively did a reorg at Netflix when we moved to this architecture, and that's one of the reasons we were able to build it and deploy it and move a lot faster than the rest of the industry. Now, if you go to a customer and say, okay, to buy my software, you need to do a reorg, it's kind of a hard sales pitch, but I'm hoping to sort of soften that for people and so that they do the reorg and then go and buy the interesting software. So this is what our organization looks like. We have a chief product officer, Neil Hunt. Reporting to him is a bunch of VPs of engineering and VPs of product management, and there's no VP of ops in this, right? There is actually a VP of IT ops who does desktop provisioning and looks after our DVD business and things like that, but he is not involved in the provisioning of our product infrastructure on AWS. The whole of that old traditional IT organization deals with the traditional IT stuff. We have a bunch of directors. They're all in the same organization. We all talk a lot. Underneath that, there's a bunch of developers. And each vertical team that's responsible for one of those services, one of the little boxes on my diagram showing you how everything worked, they own their own data source, their own deployments, their own code. They deploy at whatever rate they want. So every one of those individual little icons on that complicated-looking diagram is updating asynchronously whenever it wants. And some of those services are data services, and again, they update asynchronously. And we've completely denormalized all of our data to get to this. So all the way, sort of a vertical responsibility for deploying a new thing. That decouples everything. So that means every team can go as fast as it wants or as slow as it wants. And you're not tying the whole business together into one sort of delivery cycle. So this basically means that there are 4 transitions to get to the cloud. And the first one's a management transition. This is this reorg. Basically, you have to integrate the roles. What we did was we took the AWS budget, we gave it to development. So the development organization owns the AWS budget at Netflix, whatever it happens to be. It's now our biggest IT budget, I think. But at the time, it was like, okay, you're going to own this, you're going to pay for it, you're responsible for the IT budget. We're not vectoring this off through the IT organization. Then the developers have to learn how to deal with NoSQL, let go of all of their joins, denormalize the data, because if you've got silos of data, you can't join across them because they're all in separate databases. And it's polyglot. Some of the data ends up in MongoDB, some of it ends up in Cassandra, some of it is in MySQL. You can't do a join across them anyway, so you have to learn how to denormalize your data and how to denormalize across your whole business. So we now have 50 different Cassandra clusters running in production. Different, every one of them sitting behind a different data source owned by a different group of developers. Then the other thing is moving to continuous delivery. Like I said, we want to be able to update our code. I think we're roughly at a 2-hour update rate. If you make a change, the fastest we can get it into production, going through all of our test, QA, and deployment process is about 2 hours. So you could do, I guess you could in theory do 12 deploys a day on that model, but we're gradually speeding that up. What we actually do is approximately daily updates for some of our most active services. And those are planned updates. Those are kind of not fixing it because it broke. That's deploying new functionality. We can obviously fix things quickly if we need to. So you're decentralizing and you're letting each group go at whatever speed it wants to. And then the other thing is moving this responsibility from ops to dev. Agile infrastructure and cloud, you make it a developer responsibility. Again, that speeds everything up. Because I want hardware, it takes me minutes. It doesn't matter whether I need 100 machines scattered around the world, it still just takes me minutes. It doesn't take me any longer to provision machines in Brazil or the East Coast or the West Coast or Europe. I just click buttons and they happen. So let's look a bit at the sort of decentralized deployment model. This is the tool we built called Asgard, which is our replacement for the AWS console. And I just want to try and explain what we're doing here. If we've got a new version of our software and an old version of our software, which happens to be called Obi-Wan, because one of our groups likes to pick Star Wars characters as its group service names, we have 2 versions of this running side by side. When we want to deploy a new version of our code, we don't update the existing machines. We bake an AMI, we bake a machine image, and we deploy completely new hardware run on completely new instances running the new software. The old software is still running. Once we've smoke tested it and make sure it works, we click a button on this user interface. The developer clicks a button, pointing traffic at the new software and the old, monitors it for a few seconds to make sure it looks okay, maybe a minute or so, turns off traffic to the old one and leaves the old one there. And then over the next hour or 2, everything looks okay. Eventually, we automatically delete the old code. You can set a few hours or whatever. If there's a problem, you click a button, send the traffic back to the old version, and then work on a new update. So this way, we can incrementally push code. It's seconds to detect. It's seconds to roll back, to roll forwards. We're just pointing traffic at 2 different versions of it, and we maintain this model of all of our deployments. So you can see it's totally decentralized. There's no ops involvement, and everything takes seconds. Now, what does that really look like? So this is one of our API services. We typically start the day with about 200 servers, and we scale up to 600 and something automatically using auto-scaling. And then once we get through peak in the evening, we scale back down. And right at the end, you can see someone's doing a code push, and the number of servers just suddenly doubled because we're running 2 side-by-side versions of it. Okay? It's just to clarify exactly what that looks like. And the nice thing is that during the quiet period overnight, we're not paying for these machines, right? We're only paying for the machines we use. And then the other thing is you see machines being allocated in the afternoon into the early evening and deallocated overnight. So these are machines with a very short lifetime. And the average lifetime of instances that we have is roughly a day and a half, about 36 hours. Some of them only last a few hours. Some of them last for months. But it's a long-tail distribution. So this is all running on public cloud for us, because we're in this gray area where we're too big to be a startup, but we're not as big as the Googles of this world. So if you're Facebook, Google sized, you have to build your own infrastructure. There isn't a public cloud that's big enough to run you, and you run everything internally as if it was a cloud anyway. So this is Apple, Google, Facebook, those people. They're building their own clouds just because that's the scale they're at. We're in the sort of 10 to 20,000 instance level, which I think which is a size which comfortably runs on AWS, certainly in US East and Europe. Some of the smaller environments, they don't have quite so much stuff. So we could run our own data centers, but we choose not to. And one of the reasons for this is if we had, let's say, $100 million to spare, we could go build a big data center, but we could also go and commission a new original movie or TV show, and we'd much rather commission a new TV show because that moves our business forward rather than sinking money up front in a data center where we'd get payback in a year or two. So we like the flexibility of paying later for the compute resources we need. We're already having to commit money up front to make original content. So it's a better use of funds for us to work on a pay-as-you-go basis for infrastructure, and we can be much more flexible about where we put that infrastructure. We can upgrade from older instance types to newer instance types without even thinking about it, all those kinds of things. So how big is public? And that gray area, as we get bigger, that gray area needs to be getting bigger. If you go back 3 years, there were only about 400,000 IP addresses allocated to the entire global AWS cloud. So it had to be smaller than that. There are now approximately 3.7 million IP addresses. So over the last 3 years, AWS, by this measure at least, has grown an order of magnitude. It's 10 times bigger. So as long as they keep growing on this kind of scale, then we're okay. We're going to sit in that gray zone, and we won't outgrow AWS. So that's the comfort factor we take. So this is another problem we have, right? The strange world of broken streams, the cloud of broken streams. What happens when we go down when there's no video and your kids are at home because it's snowing or something, and you really need Netflix on those days when it's snowing outside and the kids are out of school. What we're doing here is we're working this year primarily on multi-region availability, and most of the kinds of outages that we still have in our architecture are covered by this. So we're looking at regional load balancers on the East Coast and the West Coast. We have a customer, and we need to connect the customer, route them to either side. And to do that, we need to control DNS, and we need to be able to switch things back and forth. So we built this open source toolkit called Denominator, which is an abstract Java API and command line tool, which can use any DNS vendor and can control advanced features of DNS like geo-based routing. So it looks up a customer on the East Coast and sends them to the East Coast services, looks up a customer on the West Coast, sends them to the West Coast services. So if you're doing anything that involves automation around DNS and you want to do it with Java, or you'd like to use the command line version, look up Denominator on our open source project. We went looking for where's the library to do this. There wasn't one, so we just built one. And I think we're kind of filling a need that's been out there for a while with this particular project. We do big data as well. Like I said, all our data is in the cloud, so we process it in the cloud. And big data in the cloud really works well for us because the queries and the things you want to do are kind of lumpy. There's less work going on at the weekends. There's less work going on during the day. There's all these big jobs you need to run to do daily roll-up. There isn't a constant size of work. So you want to be auto-scale and dynamically size your big data. This is our data oven architecture. From our cloud services, we're explicitly emitting events, around 100 billion events a day, through a pipeline called Ursula. And then from Cassandra, we suck all the data out of Cassandra that gives us our dimension data. By that I mean our subscriber database, because you need to know, you see an event for this subscriber ID, watch this movie. So I need my dimension data, this is the universe of subscriber IDs, this is the universe of movie IDs. We need to pull all that data in, and we do that by sucking it directly out of Cassandra using Aegisthus. Aegisthus was the person that killed Cassandra in Greek mythology, and it works off a dead Cassandra cluster because it's basically sucking up the backup files. We have a continuous backup process running into S3, so it just feeds off that. So that gets fed into S3, and our data warehouse is S3. It isn't running, it used to be a Teradata, but the master copies of all of our data in our data warehouse is now S3 based, over 2 petabytes of it, and then we treat Hadoop clusters as processing steps for dealing with that. We have like 1,300 nodes of a fixed size cluster that's doing production processing continuously, an 800 node cluster that's used for querying by individual data science users. And then every night we create a number of 150 node clusters which actually use up unused machines that during the day were API servers. Like we have reservations that we're not using at night, so we use unused reservations. Then we process them using Hive, Pig, Java, Python. With this architecture, there's a wrapper around this that we're open sourcing around the Hadoop Summit, which is coming up in June, I believe. So you'll see a lot of open source projects from us around that time. And we have a visualizer for Pig that we've called Lipstick, by the way. So it's just, we pick fun names for things. All right, so just very briefly, a lot of these tools have been released as open source. There's a lot of books I take as inspiration, so this is my reading list for everybody. I should probably put Cloudonomics on here for Joe, but I'm sure we've all read Cloudonomics already. This is much more about the architecture of how we build things, so release it, drift into failure. If you're flying on a plane, don't try and read Drift into Failure. It's full of stuff about air crashes and people dying in hospitals and things, but it's a really interesting book. Anti-fragile is the core idea behind a lot of this architecture, a lot of the chaos engines. And if you're designing APIs, go get George Reese's book and give it to your engineers and say, please don't make any of the mistakes, because he lists all of the bad APIs that he's ever dealt with. George is the CTO of Enstratius, who just got bought by Dell. He's built an API to every cloud vendor, and he has just like a litany of terror of all these horrible APIs and all the things that you should do right. So our platform we built started off as this bleeding edge innovation platform 2009. Then it became more of a pattern. And what we're doing now is we're really turning it into a shared pattern. So there's commoditization, and we don't think of a platform as being a differentiator for us. It's something we had to build that we now want to share because we're trying to build an ecosystem around it. So we're trying to, the goals we have for open source are to establish these as best practices, to figure out whether what we've done is a best practice, you release it as open source and see if people use it. We're also using this as a hiring mechanism. Our top engineers really like to work on open source projects, and the good ones have open source projects to their name. We're also building up the Netflix technology brand, and then we're building this shared ecosystem of bug fixes, ideas, portability to other platforms. So how does this all fit together? We have, I don't have time to go through all of the different projects we have, but we have this example application, which is a bit like Google Reader, but it's built out of all of these Netflix projects. And you can see all of the names that are in purple on this. Each one of those is a separate Netflix project. So Eureka is a service registry. There's a client library, a server-side library. There's logging. There's a base server. There's a thing for feeding autoscale metrics. There's a Cassandra client library, and lots of other stuff. So this is a subset of the projects that we have sort of wrapped around and put together so you can see how to use them. So in order to boost this ecosystem, we came up with the idea of having a prize. So very quickly, we have all of these different categories that we've got prizes for, and Joe's one of the judges for this. So we have a total of 10 different prize categories that we're looking for. The These are the 6 judges that we have. My manager, Joe Werner-Vogels from Amazon, Aino Corey from QCon, Simon Wardley and Martin Fowler. They're going to decide who wins. And this is basically how it works. We launched it on March 13th. We have a few hundred people that have entered it so far, but developers procrastinate, so we're giving them till September the 15th. And there's going to be an award ceremony and a dinner and things like that at the AWS reInvent conference in Vegas. So you win a trip to Vegas, $10,000 in cash, and $5,000 of Amazon credits per, times 10. So the total investment in this is roughly 200K. And we're hoping that we'll get more than 200K's worth of engineering and press and awareness out of this. That's the basic idea. So, last couple of slides, and I'm out of time. We have functionality and scale now. We're working on portability. The latest version of Eucalyptus runs Asgard, runs some of our tools. So we're starting to see some of the cloud vendors that are supporting hybrid and data center-based clouds running the Netflix tools. We're also talking to various OpenStack people and CloudStack and some of the other cloud vendors about running our tools. We're moving from a bunch of different projects to a platform, building an ecosystem, and the whole thing is evolving very rapidly. So if you start using this stuff, you'll find, we're updating stuff quite often, and it's adding features, and we've got lots more projects to still release. So this is my takeaway. We're making it easier for everyone to become cloud native, and we're using open source not just as a default, but as a strategic weapon, as a competitive weapon. Some of our competitors that we care about from an engineering point of view are the other companies in the Bay Area that we're trying to hire, hiring competition, and some of them are more technology competition, trying to just figure out ways to make the way we use the cloud into a default way so that other, the cloud vendors start to build tooling around the way we want to use cloud. And it's not just for Netflix, it's for a larger group of people that are doing cloud native. Be happy to connect to anybody on LinkedIn, and I'll be around for the rest of this morning. Unfortunately, I have to leave before lunch, so sorry about that. Thanks very much.